In this video, I'm going to go over how to use the sound library in processing. This is a sketch that's taking live mic input and it's responding. You can see the circle is getting larger as the volume increases. So let's go over this code quickly and then we'll start to add on to this and do some variations. So this is actually just mic input sketch. We're importing the processing sound library up here. You can always do that by going to import library, and this is one of the basic installed libraries that comes with processing. We're also going to create these objects here. We're going to create something that's called an audio in. We'll give it a name or we're going to specify input, and we're going to grab this amplitude object and call it analyzer. And so what we're going to do is declare these objects here. You can see input and analyzer were created. I'm creating a sketch that's 500 by 500. What we need to do is this object here, input, we're going to create a new audio in. So this is the type of object it is. Again, we'll just say this to specify it's this specific one, and we'll write 0 here to grab the first channel of the audio. What we want to do is start analyzing or start bringing in the audio input. That's what this code is saying, and we're going to create this new amplitude analyzer, so you can see that the code is similar. And then what we want to do is specify that the input, in this case, it's a little bit confusing because it says input twice, but we're running this function input, and we're telling it to grab this audio in, this input here, which we've specified as the first channel. Okay, so from there, what we're going to do is take the volume. We'll create this variable volume, and we're going to get the value of that by running this analyze function on analyzer. I like to print this to the console here, so it gives me an idea of what my values are, because depending on your mic or the sound, the level of the sound, you might get different values, and sometimes when you're writing the code, you might remap things. So what I'm doing here is creating this variable R for like the redness of that circle, and I'm remapping it. I know that volume goes between 0 and 1, but honestly, most of the time it doesn't really get that close to 1. And I'm mapping it from 100 to 255, right? Again, if I was just put in volume here, it'd be such a small value, I probably wouldn't see it. And then diameter, I'm using that to drive the size. And here you can see that I maybe was a little bit more sensitive with it. These numbers here, you can see there's nothing that's really close to 1. So I made this 0 to 0.2, and maybe it's, it works. It's more responsive. If I put 1 here, it would be less responsive. And I'm saying it could be as small as 10 up to 400. And that's pretty much how that works. And again, this is the sketch, and you can see it responds. If I clap, that's getting pretty loud. Yeah, and it gets big. Yeah, I wanted to do a variation on this because one thing I noticed is it's a little bit jerky. It's it's just responding to the sound, and sometimes it looks like it's kind of bouncy, or it's just kind of it looks like it flickers a little bit. So what I want to do is create a version that uses easing in this to create a more smooth motion. So I already have this sketch built out. Let me play this first, and then we'll see the difference. You can see what happens is when it moves into, when it moves between values, it actually, it eases into that motion. It doesn't just, jump right away to that next value. It kind of moves slowly and it kind of slows down, or, it feels smooth. It feels more organic. So I'm basically going to take this sketch and I want to just show the differences here between these two to give you an idea. So a lot of this is the same. The difference is I have some extra variables here. I have a variable called easing, which I'm going to use as my like easing, I guess, coefficient, or this value that gets multiplied. And one thing you can think about is the lower the value, the more smooth it is. So if it's at 0.5, it's going to be a little bit it's less smooth, a little bit more jerky. 0.1 is pretty small, so it's going to be a little bit nicer. I also want to make another variable, my diameter that's adjusted after the easing has happened. So this part is the same. Where does it change? Well, down here, what you're going to see is basically underneath these this code here, we have the diameter, and that's actually pretty similar. This code, and if you look up just processing.org and look at easing, this code is kind of taken from there. Basically what you do is you take a target value, I would call it target D because it's meant to be the diameter, and we're going to set it equal to the diameter, and that value is being piped in through here. And then we're creating this like difference between the diameters, and so it's diameter minus the diameter adjusted, and then we'll say the diameter, we'll change the value of the diameter adjusted, we'll say plus equals this sort of like difference times that easing coefficient times that value. Again, this code, so you would just use this in your own way. What you would do is, you have this target value, and then you could do this. It could be something else. It could be like a bouncing ball, or use mouse X and mouse Y. What you'll do is you'll have your target X maybe, and then your X value, your mouse X, and you'll use that to with this code like this. Maybe it would be dx or something for the difference. So diameter, and it might be like mouse X minus your mouse X adjusted, right, or the other value. And then you can see when we draw the circles, we're using this adjusted value here. So that's the main difference. And again, for me, this is a little bit smoother. It adds a little bit more refinement to the animation. So I think it's something that's good to try to put into it. And there are other applications certainly beyond using it in sound. Another thing we can do with sound is not just analyze the amplitude of it, but look at the frequencies themselves and start to kind of dissect the sound. Here you can see kind of like a frequency analyzer. Most of the frequencies are up on the left-hand side, but if I make a higher frequency sound like s, you can see that the frequency shifts a little bit. So let's go over how to do something like this. This is a pretty standard setup. Again, we're going to use the processing sound library. What we'll do is follow some of the stuff that we did with the mic input, but then we're going to use this FFT object. FFT stands for fast Fourier transform, and it again refers to sort of like breaking something apart by the frequencies. So we have this variable bands right here, and this is giving us how many of those bars that you saw. And there are, I believe, 512 bands that we can look at, but we might not need that much detail. So I've divided by 4, but you could go up to 512, or you could go to, divide this by 2, depending on what you needed. So this sketch is 512 pixels across. This should look familiar to you. We're saying input equals new audio in. This and 0 grab the first channel. You can see we've initialized it or declared this input up here. We'll start again the audio, and here's where it changes a little bit. We're going to create this FFT object. So new FFT, this, and how many of those different frequencies are we looking at? So we're going to feed bands into it. And again, I said it could be up to 512, but we're gonna do a few less. And what we'll need to do is, instead of doing amplitude here, or instead of analyzing that, using the analyzer and looking at the amplitude, we're going to use FFT, and the input is this input that we've created up here. Again, in the draw, we're going to run this analyze function, but we're running it on this FFT object to give us that ability to look at all those bands. And then we're using a for loop to draw all those bars, and the bars, you can see, will be the length of them will be mapped here. You can see, because the range is going to be between 0 and 1, and what we're going to do is kind of multiply, map it out 0 to 1, and we're going to say remap it to 0 to height. And that Y value is going to let those bars change their height. You can see here we're using I to evenly separate an increment across. We're taking width divided by bands. That's the width of each little piece of that spectrum. And yeah, this is the width again, and you can see this Y value, and I'm printing that out here. Print line the Y value. I'm printing this out. So again, let's look at this, and you can see where we're able to look at the different frequencies here. In the next example, I'm going to do something different with this, but use the same framework to create a sort of another sound visualizer. All right, so let's take that previous example and make a different type of visualizer. We're going to use FFT again, so we'll keep a lot of this code the same. What I'm going to do is change the number of bands here, so we have a few more. So instead of drawing sort of a horizontal line, or like drawing the bands horizontally, what I'm going to do is rotate them around. I think what I can do is start with the push matrix. We want to start with a circle centered in the middle of the composition, so we'll do width divided by 2, height divided by 2, and then we'll rotate. Now 360 degrees is 2 pi. We're going to divide that by the number of bands that we're using and multiply it by I to incrementally rotate around this circle. From here, let's maybe we'll keep it at stroke 0 for now. We just want to set this up. Float Y, we can see what that looks like. We have this rectangle. Instead of a rectangle, I'm going to use a line. So maybe I'll start at 100. That's the offset of the circle, and maybe it's 100 plus Y. Let's see what that looks like. Let me delete this, and at the end of this, I want to make sure that I'm using a pop matrix to get rid of those transformations. Let's just see what that looks like. You can see it's around the center and it's moving, or the bars are moving. Yeah, so this is the initial setup. Let's go in and style this a little bit more. One thing I'm going to do is actually change the color mode in this case to HSB. This is going to let me create sort of a rainbow-like spectrum. So 360 degrees of color, 100 saturation, 100 brightness. Okay, let's go down into here. So here, let's change the color of the stroke. We're going to map this I0 bands. That's the minimum max up for I. And let's go from 0 to 360. And we'll map that. So that gives us the full 360 degrees of color, 100 for saturation, 100 for brightness. And we can play around with this. Like if we, maybe we wanted to start somewhere like 10, and I think the height right now is 540, but we could even bump this up a little bit more to something like 800 with the line. And we could even, if you want this to be more responsive, you could multiply it by another number here. And yeah, let's just see what that looks like. Yeah, so now we have this color spectrum, and you can see, the degrees of color are moved around. We might want to do some other things here. I'm gonna maybe throw in some noise and maybe I'll use theta as well to rotate this around. So float theta and t. Let's see what else we could do. One thing we could do is add on rotation. So let's say we wanted this thing to just keep rotating. We could add theta here and do a little increment. Let's add some noise here, and maybe we'll just throw some noise on the line. Maybe here we'll add noise T times 50. So remember, noise only runs from 0 to 1. So if we want to see something, let's take a look at that. So now you can see the circle is just kind of moving on its own a little bit. There's a little bit of noise there, and it's just kind of moving at a constant rate. But we could even do something like grab the and we'll say plus equals. Maybe we can grab one of the channels for the spectrum. One of the bands, I guess. I mean, you could put in any number here. Maybe I'll just say 10, but you probably could put in any number here up to the number of probably 512 or the number of bands. So we'll do this times. Let's try this. This should be more responsive. So as I make sound, you can see it's moving a little bit faster. So it's a way of visualizing the sound. And if maybe I just want to change the background real quick before I, maybe it's something like this, a darker color. There we go. So it's a little bit more contrast, and you can see this is responding to sound and moving. Yeah, so just another way to visualize sound using the fast Fourier transform. In the previous examples, we've been using live mic input, but another thing you might want to do is actually play a song or an audio file, in this case an MP3, and I wanted to show how you can go about doing that. The setup is pretty similar. I'm actually using a sketch, a previous sketch as a base, and all I'm doing is plugging in the MP3 instead of the live audio input. So the difference is, well, I guess we'll just talk about the setup. Again, import your sound library. We're going to create this sample object. It's a type sound file, and we're going to call it song. The amplitude analyzer we've set up before. This example is going to use easing as well, so we're going to have these easing variables at the top. Now what you'll do is you've declared this object song, so we're going to create a new version of this. So new sound file. Again, we'll use the word this, and then this file right here is in the data folder of the sketch, and put it in quotes. It's an MP3 file, and we're going to play it. Now you could write just play or loop. In this case, if I let this keep going, it would just keep looping, but you could also write play. And this amplitude analyzer we've done before, this is where it kind of is a little bit different. Instead of saying input, which is, in the past we had like a live mic input, we're gonna patch in song. So this variable, this object up here. And from there, the setup is pretty similar. We're doing an analysis on the to get the overall volume. We have some code for easing so that that circle is moving a little bit more smoothly. Yeah, and that is pretty much it. I've mapped this out a little bit. One thing I noticed is that the mapping values I needed to change. When I first ran the sketch, the circle was getting a little bit too large at some of the higher volumes, and that has to do with, again, the type of sound that's coming in. I think also processing is able to read these files maybe at a higher volume. So I did adjust the mapping here. And one thing I do is I like to print out the volume value, so I get a sense of what the minimum maximums are. And you can see that these values are a little bit higher. I mean, some of these are above 0.5, so I could have actually gone above 0.5, but the original value I had, I believe, was 0.2, which might be okay with sort of softer mic volumes, but with louder music, you might need to adjust this. Yeah, so this is just an example of how to play back sound. I mean, if you just wanted to play it, you could just do something like this, but to analyze it, you're going to patch in this song variable. One other thing that we can do is with the sound library is to actually create sound, produce sound using oscillators. In this sketch, I have 5 different types of oscillators: a sine oscillator, triangle, saw. These correspond to the types of waves: square and pulse. And what I've done is I've created these oscillator objects down here or up here. We need to initialize them here, and you can see that I've done that. I could start playing them right away, but I've actually made some key presses that allow me to turn these on individually. You can set things like the amplitude or envelope or other function or other properties, and you use dot syntax here. So the amplitude is how loud it is. I'm setting it to 0.5. Okay, and then down below, what I've done is I've mapped the frequency. Now, sound has a frequency. The lower the frequency, in terms of the number, the lower that sound sounds. A high frequency has a higher frequency, and these frequencies actually correspond to musical notes. So, for example, a common tuning benchmark is A at 440 hertz. Yeah, so what I've done here is taken the frequency, mapped it to the mouse position, mouse X, and I'm piping that into the frequency that will play. I'm also using a circle to kind of let me see where my mouse is, so I can control it. And in a void key press, I've created these different conditions. When I hit 1, oscillator 1 will play. When I hit 2, oscillator 2 will play, and so on and so forth. And there's one little condition I wrote is I don't want them to all start play all on top of each other. So I've created this bit at the top. Whenever I press any key, it's going to stop all the oscillators, and then if one of these keys is selected, then it'll only play that one. So here's an example of what this sounds like, and I'm going to be pressing different keys and changing the types of oscillators so you can hear how the sound changes.